Alright, so in this section we are going to start off by letting f of t be an impulse force of magnitude we'll call the magnitude h, and we're going to say it's lasting epsilon seconds. Okay, so that's the Greek letter epsilon. Okay, and we use that letter because in practice, epsilon is going to be very small. Okay, um, this would be like the force of hitting an object with a hammer. Um, the duration of that force would be very small, because if you think about it, like if you hit a mass with a hammer, or if you hit a baseball with a bat, um, the bat is in contact with the baseball for a very short amount of time, so that force is really only occurring for a very short amount of time. um, the graph of that would look like this. Here's the t-axis. My force is going to be, it's going to be 0, and then all of a sudden it's going to jump up and have magnitude h, and then it's going to be 0 again. Okay, and so it's a piecewise graph. It's 0, and then it jumps up to a constant h, and then it goes back to 0 on the t-axis right there. So our impulse force, it starts at 0 seconds and it ends at whatever epsilon was. Okay, which is a very small positive number. Okay, we define the impulse, the actual impulse, of that force. We'll call it capital I. Define it to be the integral from 0 to infinity of f of t dt, which, if you think about it, integral of a function's area under the curve, and really, the area under the curve, there's only a little bit of area. It's this little rectangle here. And we could easily calculate that. The area of the rectangle would be height times width. In this case, it'd be h times epsilon. Okay. What we would like to do mathematically is we'd like to imagine this with epsilon being extremely small. In fact, basically letting epsilon go to 0. Okay. So we define what's called the Dirac-Delta function as by letting epsilon go to 0, or I guess as an impulse force with epsilon going to 0. With impulse actually equal to 1. Okay. So in other words, the the integral and the Dirac-Delta function, we have terminology for it. It's we use the Greek letter delta. delta of t, right? Delta of t is the Dirac-Delta function. It's an impulse force with impulse 1. So what that means is that the integral from 0 to infinity of delta of t dt is equal to 1. Okay. The graph of it would look like this graph, except for we're letting epsilon go to 0. Which if you think about it, if epsilon's going to 0, but the area of this rectangle is still 1, that means that the height would have to be getting bigger and bigger and bigger. Okay. So another way to think about delta okay, the delta function is going to be 0 for almost every single t value. Right, for any t value, for anything other than 0, the delta function is going to be 0, right? Because the graph is going to look like this, flat line is 0 here. Except for at 0, you've got, kind of a really, really, really thin rectangle with area 1, which means it has to be really, really high. And so the only thing that really makes sense for the function value there would be infinity. Okay, that's basically the definition of the delta function. Of course, that's not really a great definition because infinity is not a number. So this is, it's really not a function per se, but it is a good mathematical tool for modeling impulse forces over very, very, very small periods of time. Okay, hitting an object with a hammer, hitting a ball with a bat, the voltage surge from a lightning strike. Okay, that kind of thing. Okay. Now, so that's right. That's what delta of t is. So what would delta of t minus a be? Okay, well that would be like a horizontal shift of that graph. It's going to be 0 if t is not equal to a, and it's going to be infinity if t equals a, right? Because that's what would make the input of that function either 0 or not 0. And what I want you to do is I want you to recall from last section the unit step function u of t minus a, right? U of t minus a, what was that? Well, that was either, that was, a slightly different looking function. That was 0 if t is less than a. It was 1 if t was bigger than or equal to a. The graph of it, the graph of the unit step function looked like that. Okay. And what I want you to notice is that the unit step function, the slope here is 0, the slope here is 0. So that means the derivative of the unit step function is 0 over here, it's 0 over here. But then it's, there's like a vertical jump here. So it would make sense that the derivative, if it's going straight up, it would, the slope would be infinite. Okay. So, the slope is 0, infinity, and then 0. That's exactly what the delta function is. Okay. So a fact is that delta of t is the derivative. Well, here, delta of t minus a is the derivative of u of t minus a. Okay. I am going to put derivative in quotes there because it's not, it's not technically the derivative, because technically, this unit, a function that's not continuous, it's not differentiable. Um, but if we had to define the derivative, if we had to say that the derivative was something here at a, we would say that it's infinity, which is basically what the Dirac-Delta function is. Okay, so it turns out that if we kind of just take that to be true, um, then we get some nice results in terms of Laplace transforms, which are actually very useful for solving differential equations. Okay, so